All right, if you're learning to fly, you've got to know that the atmosphere is your playground, it's your highway, but it can also be your biggest challenge. So in this explainer, we're going to take a virtual flight straight up, from the runway all the way to the edge of space, just so you can build a really clear mental map of the air you'll be flying through. Let's start our climb.
You've definitely seen this, right? A huge thunderstorm cloud just boiling upwards, and then, poof, it spreads out into that classic anvil shape. So why doesn't it just keep going up forever? Well, the answer is all about the basic structure of our atmosphere. And you know, understanding this is really key to predicting weather. By the time we're done here, you'll know exactly what that invisible ceiling is. Okay, so the second our wheels leave the runway, we are climbing through the first, and honestly the most important layer for any pilot, the troposphere. Just think of it as the atmosphere's action zone. It's the part that's touching the Earth, and it's where we live, where we breathe, and where we do pretty much all of our flying. Now here is the #1 rule of the troposphere you have to remember. As you go up, it gets colder. We call this the environmental lapse rate. Now it can change a bit, but the standard, kind of textbook rate, is a drop of about 2 degrees Celsius for every 1,000 feet you climb. This constant cooling is basically the engine that drives all of our weather. So why is this layer so important? Simple. Because everything we call weather, clouds, rain, thunderstorms, wind, turbulence, almost all of it is happening right here in this layer. The troposphere is a messy, dynamic place, and being a good pilot means you have to understand how it behaves. So we keep climbing, right? And the temperature just keeps dropping and dropping until, all of a sudden, it stops. We've just hit the top of the troposphere. This boundary, it's not a wall you can see or anything, but it is one of the most important features of the entire atmosphere. Welcome to the tropopause.
And here it is. This is the answer to our first question. The tropopause acts just like a lid. The temperature stops getting colder, and that change basically puts a cap on the powerful updrafts inside a thunderstorm. It forces the cloud to spread out sideways. It really is the top of the weather machine. It's also where you find the absolute coldest temperatures, and for you high-altitude flyers, this is critical. The powerful jet stream winds are usually roaring just underneath it.
Okay, pop quiz. Thinking about the planet, where would you guess the air is coldest at this ceiling? Would it be over the freezing poles or over the hot tropical equator? Think about it for a second, because the answer is probably not what you expect.
So believe it or not, the tropopause is both highest and coldest right over the equator. We're talking a staggering -75 degrees Celsius up there. But why? Well, all that intense heat from the sun at the equator literally pushes the entire weather layer much, much higher, which gives it more altitude to cool off before it finally hits that ceiling. Over the poles, the tropopause is way lower and, surprisingly, a whole lot warmer.
Now, if we were in a jet or something with a bit more punch, we could push right through the tropopause and enter a totally new world, the stratosphere. And let me tell you, the second you cross that boundary, everything changes. The air becomes incredibly stable and just smooth. So here's the biggest difference, the one thing you need to remember. Remember that lapse rate in the troposphere? As you go up, it gets colder. Well, in the stratosphere, that rule gets flipped completely on its head. As you climb higher into the stratosphere, the air actually gets warmer. And that's why the air is so stable here and why weather just doesn't happen. So, what's heating this layer up? The answer is the famous ozone layer. This layer of gas is like a fantastic shield for the planet. It absorbs all that harmful ultraviolet radiation from the sun. And in the process of soaking up that energy, it heats the atmosphere around it, which is what creates this totally backward, upside-down temperature trend.
Okay, so we've climbed up to our cruising altitude. Now it's time to start our descent and see what kind of trouble we might run into on the way back down. We've learned the rule, right? In the troposphere, temperature goes down with height. But a safe pilot always knows the exceptions. And the most important exception is something called an inversion.
An inversion is, well, it's basically like a little slice of the stratosphere, but happening way down low in the troposphere. It's a layer where the normal temperature drop flips, and you get a layer of warm air sitting on top of cooler air. And just like the tropopause, this creates an extremely stable pocket of air that acts like a lid.
As a pilot, you're really going to run into two main types. First, you've got the ground inversion, which usually forms overnight right near the surface on clear nights. And second, there's the upper air inversion, which forms higher up and is usually tied to big areas of high pressure.
A ground inversion on a cool morning can be a serious problem.
That lid effect traps all the pollution, smoke, and haze right near the ground, which can create smog and just kill your visibility for takeoff. You might also notice that the winds are calm at the surface, but then you climb through the top of the inversion and bam, you hit significant wind shear.
Now, an upper air inversion gives you a totally different set of problems. You could be flying along in beautiful, clear air on top of it, but as you descend to land, you suddenly punch through that inversion layer and find yourself in a thick soup of haze with visibility that drops like a rock. It's a classic trap for pilots who are on approach.
So, let's bring it all home. Here's the most important takeaway. Understanding the standard layers, troposphere, stratosphere, that gives you the basic flight plan for the atmosphere. But knowing the exceptions, like these inversions, that's what prepares you for what it's really like to fly out there. And it's what helps you make safe, smart decisions.
So next time you pull up a weather chart that shows temperatures at different altitudes, don't just see a bunch of numbers. See the layers. Look for that Tropopause height. And more importantly, be on the lookout for those telltale signs of an inversion. How is this new mental map going to change the way you get ready for your next flight?